Hey y'all, Dr. Taylor back with you here. We are in Module 4. Today we are going to cover Chapter 11, which in general covers a couple of big key concepts in making sense of data. So this module is about making sense of data and then being able to interpret some very basic statistical relationships between two variables. And all of that will be explained in some detail, particularly in the next video lecture podcast. So, but for this chapter, Chapter 11, we're mainly going to focus on central tendency and dispersion. And after reading this chapter and after going over this lecture, you should be able to explain how to compile a data matrix and summarize large batches of data. We're going to be able to describe statistics for measuring central tendency and variation or dispersion, relate how to graph data for presentation and exploration, and then summarize the early steps in making sense of data to lay the groundwork for statistical inference. So basically, this is the next sort of baby step. Now we've gone over so far how to think about a research design, experimental, non-experimental, case study, qualitative, quantitative, a lot of different avenues for you to go. And regardless of your research design, you will be gathering data in some way. You will be gathering it from the written record. You will be gathering data either from an episodic record or an official record of some sort or another. And then once you have those data, you need to be able to make some sense out of what they are telling you. And the way we do that is with numerical values. And so that's what central tendency and dispersion are all about. So central tendency, dispersion, and understanding concepts related to those things are about beginning to get an understanding about what data are telling you in a quantitative numerical format. So, and even if you do qualitative work, even if you're doing case studies, if this is your avenue, you may end up having to do some very rudimentary quantitative steps like mean, median, mode, measures of dispersion, things like that. So this chapter is valuable regardless of your general research strategy and your research design. So the first thing we want to do is talk about description. And we can describe data in a number of ways. We could describe every observation or every value in a data set. But the problem is that this would be overwhelming and generally unhelpful. If you think about what a data matrix is, a data matrix is a set of columns and rows where you have variable labels and then the values for each observation underneath those labels. And that becomes, if you wanted to go and sort of talk about each of those individual variables, that would be very cumbersome over time. And we're going to look at some data matrices as we move forward. From your textbook, I'll talk about them as a data matrix. But you can think of an Excel spreadsheet as a data matrix. It's just a series of rows and columns with variable labels at the top, some observational identifying information, a number, a code, a name, something on the left-hand side, and then each row is filled with an observed value for every variable for that observation. So again, we'll talk about that as we move forward, but that's what a data matrix is. And you could go through and describe all of those observations in each individual piece of data. Each datum, I suppose, is the singular of data. But that would be, well, in the end, you wouldn't be able to say very much because you wouldn't get very far. So we want to use these data matrices. We want to be able to describe data in a holistic way. And the way you do that is with a data matrix. And this is an array of rows and columns that store observed values of a variable. And again, we'll look at some of these in a moment, but this is how you have to organize your data. So in this class, you will not be required to do this. We're just talking about it now so you have an idea about what we're talking about and why we're talking about it. But in future classes, you may be required to gather your own data, to organize it, and in some way put it together. And so you'll be using a data matrix. And once you have your data in a matrix, you can describe it in a number of ways. Excel is wonderful by putting together graphs and other things, bar charts, pie graphs, dot plots, etc. We'll look at some of these in the end. But graphical summaries are fantastic. If you can say and explain your data with a graph, you're going to be better off than you are with statistical summaries, which are valuable and important, but they're not as useful as a graph. Graphs are the best possible way to explain your fundamental point to your audience. When you can use a graph, you should. It may be required of you to use statistical summaries to make general points and then get into more specific points about the relationships. Statistics are fine for relationships, but if you want to demonstrate the overall point of your findings, graphical summaries are going to be more valuable in the long run. But before we get to graphs, we do want to talk about some of these statistical summaries. So we're talking about frequency distributions and descriptive statistics in this chapter. Descriptive statistics, otherwise known as summary statistics. So summary statistics and descriptive statistics are going to be very, very important for you to get your arms around what your data are telling you. This is not a great way to specify a relationship, but it is a good way for you to get a general sense about what's going on with your variables. In particular, if you care about your dependent variable, this may be a good way to do it. Or again, if you care about any individual variable, so your dependent or independent variable alone, not as a relationship to each other. So this is a tricky point. Statistical summaries are we're talking about one variable at the time, right? One variable at the time. So frequency distributions these are sometimes tables that show the number of observations associated with each value variable. They could include statistics like the relative frequency proportion or percentage or missing values or odds ratios. And then we get to descriptive statistics, which is where we describe large amounts of data with just one number. So we're going to look at both of these. So I'm not going to spend a lot of time talking about these right now, but frequency distributions and descriptive statistics are very, very helpful. And you can do these with statistics, you can do them graphically, either way. Usually in tandem is best, but like I say, your fundamental point, graphs are the best. But when you're talking about this kind of thing, and you're dealing with descriptives, you may just want to use the numerical values. So there are two classes of descriptive statistics that we're going to talk about and the chapter really focuses on. Number one are measures of central tendency, and number two are measures of dispersion. Central tendency and dispersion. Measures of central tendency, this is a fancy way to say things that you already probably know a lot about. If you've been through the 5th grade, then you know what these things are. We're talking about the mode, mean, and median, although I just messed that up. It's mode, median, mean here, but you always say like mean, median, mode. But the mode is actually sort of the most important. The way we have it organized here, we go mode, median, and then mean. This direction, mode first, then median, then mean. This is the more least sophisticated to most sophisticated way to think about these measures of central tendency. So even though we rarely talk about them in this order, this is the more appropriate way to think about them. So let's get started with the mode. What is the mode? Well, the mode indicates the most common observation. You have a range of data, right? For some observation, for some variable, you have a series of observations, and you want to know what the most common observation is. There's some resistance to outliers here. By definition, the mode cannot be an outlier, so this means that you're not going to get some wildly unrepresentative datum as your mode. And so an example could be like this. So imagine you have a random sample from the United States of 10 states GDP in the U.S. in thousands. And so here they are. You've randomly sampled these 10 states. Who knows which observations they are, but you've randomly sampled these 10 observations for this variable, state GDP. And you notice that of these states, you have 1,200, 1,230, 1,230, 1420, 1420, 1420, 1560, 1580, and so on and so forth. What's the most common observation? What's the observation that shows up the most often? 1420. And so 1420 would be your mode for this range of data, for these 10 randomly selected states. That would be your mode. It's just that simple. I mean, that's all it is. The most common observation. So I'm not going to go forward here. I mean, this is just what it is. So you might say, well, the modal category, the modal observation is 1420. So if your state randomly selected has a state GDP of 2,400 in thousands, right? So then all of a sudden you might say, oh wow, this state's it's way outside the modal category. So that's important. But again, it's just one observation. The mode does not tell you a great deal. The mode just tells you what the most common observation is. So we can know, how many states are modal or not. I mean, that again, it's just a very, very rudimentary, very unsophisticated measure of central tendency. Now, the median is a bit more sophisticated, and the median is very, very helpful in certain circumstances. So the median describes the middle value in an ordered set of values. It's important to rank order the values first. So if you're trying to find the median of a specific set of values, then you want to make sure that they are largest to smallest, or there's some order to them, right? So the median is mathematically considered, it is the number of observations plus 1 divided by 2. All right. So I'm sorry. It's the median is the sum of all observations divided by 2. So what's the middle category? And even in an even set of observations, you average the middle 2 categories. So this has some resistance to outliers. By definition, the median is not an outlier and only includes one value. So what are we really talking about? How do we look at this graphically, or visually? And again, this is from the book, so this tells you how it's done. So for one, you sort the values. There's an odd number of cases. You locate the middle value, and that's your median. If there are even values, you locate the middle 2 values, take the average of those, and that's your median. But if you look at this, so this is community A, community B. So these are average house prices. These are house prices in these communities. And if you were to look at these 2 values, you will see that this is important, particularly when you think about trying to use median versus mean. Like, what's a better representation of the measure of central tendency of a set of observations? Well, in community A, over here, this first column, community A, the lowest price, we have 10,000, 10,000, 12,000, 18, 20, 22, 25, 28, 30, and then 200,000. And then over here we have the exact same units. We have the exact same, housing price or housing, worth all the way down to the bottom. The 10th observation here is 30,000, whereas the 10th observation here is 200,000. So obviously, the reason median is really good, if you took the average of these, the average of community A is going to be wildly higher than the average for community B. Wildly. This would be like living in some very, very middle-class neighborhood and having Bill Gates move in, right? Bill Gates was in your neighborhood. He can buy $200,000 house. So probably Bill Gates is a multi-billionaire, right? And so, he's going to drive up the quote-unquote average house price. So average home prices, the mean house price, is not such a great value for this. So what we want to do then is take the median. And the median for both instances is going to be 21,000, right? If you take the median for both these sets of observations, you're going to get the same median, which is going to give you a better sense of the measure of central tendency. Because just because one person in your neighborhood has a house that's $200,000 doesn't mean you live in a neighborhood full of $200,000 houses. More likely, based on these values we have in these 2 sets of observations, more likely the average, the median house price is a better sense of what the neighborhood is like. Somewhere around $21,000. You got some cheap houses, $10,000. You got some expensive houses, $30,000. There's a $200,000 house in somebody's neighborhood, but that person, probably overpaid, if we're being honest, right? So this shows you how median can be a more sophisticated measure of central tendency. And though we haven't talked about mean just yet, we will just momentarily. Median is a much better measure of central tendency if you suspect there is some type of skew in your data. This observation, this $200,000 house price, has introduced skew into community A versus community B. Community B is probably normally distributed, perfectly normal, but community A probably has some very significant skew happening. And so that's going to be very important. If you think there's going to be skewness in your data, then you want to think about which measure of central tendency is best, median or mean. And when you have the median, you can then do some really interesting things with interquartile ranges. So an interquartile range is, what happens is if we want to sort of get a sense of how our data are arranged, right? Are there more towards the top end or the bottom end of our data sets? Are they evenly distributed, or are they sort of bunched up together? We can create these interquartile ranges. So this is actually, you want to think about, this is a data matrix, right? So we have Gini indices, Gini coefficients here. So this is a measure. Gini coefficients are a measure of inequality in a given nation state. And so the more equal states have lower Gini coefficients. So high Gini coefficients mean your society is relatively unequal. Lower Gini coefficients mean that your state is relatively equal, or there's some level of equity. So Denmark, Japan, Sweden, Norway, Finland, these are very, very egalitarian states. As we go down here, Austria, Italy, UK, New Zealand, US, these are less equal states. But the question is, well, you see the lowest Gini index is 24.7, the highest Gini index is 40.8. All right, well, that sounds like a big deal to me. Maybe it's not a big deal. I'm not really sure. And so one of the good ways to think about whether or not a given observation is significantly different than other observations is to create an interquartile range. And so what we see is that the median Gini coefficient of the range of the given data set of states that we have is France at 32.7. So they're the median, and they're right in the middle, right here, right, 21. 11. They're the 11th spot of 21 observations. And so the interquartile range then becomes, we want to take the median, so everything from Canada, so you can think of Canada to Denmark as another set of data, and Belgium to the US as another set. And you want to take the median of each of those new sets. So the median here is Spain, 34.7, and the median up here is Germany at 28.3. And so to get the interquartile range of the Gini coefficients of the data given the data set we have for the given nation states we have, we take the highest level of interquartile, so 34.7, Spain's Gini coefficient, minus the median, the quarter one observation, the median for the first half of the data, 28.3, and 6.4 is our interquartile range. So for these data, we have a median of 32.7, Gini coefficients, median 32.7, with an interquartile range of 6.4. That means that in some sense, we now have a better analytical tool to use to situate ourselves when we think about how outside of the median is a given observation's Gini coefficient, right? So we know that Italy, UK, New Zealand, the US, these are more unequal societies, but how much more unequal? Well, we understand, given that the interquartile range is 6.4, that there's a relatively small window, a relatively small interquartile range. And so most states are sort of lumped in around. And so around 32, and sort of a very sort of a moderate gap there, 6.4. And so in some sense, the United States' score down here of 40.8 now demonstrates itself to be, interestingly, quite outside of what we would have expected. It's not anywhere near the interquartile range. And so the result then is that this is a way to get a sort of qualitative sense using quantitative tools of how outside the mainstream, if you will, a given observation is. But again, this is all very descriptive. We're not actually saying anything substantive about the relationship between the U.S. and Spain, France, Germany, Denmark in terms of their Gini coefficients. We don't have any statistical tests yet to use to describe these relationships. All we know is that we can now get a more qualitative sense of how far away some states' Gini coefficients are from others. And so sometimes the most sophisticated way to talk about measures of central tendency is to use the mean. And the mean is otherwise known as an average. And you all know how to compute this, right? And so I'm not going to waste your time. But there are two different means we care about. We have sample means and population means. And the difference is extremely subtle. It only becomes important when we talk about standard deviation and a few other things that we'll talk about later in the next module. But there's a sample mean and a population mean, but in a sense they're the same thing. You take the sum of all observations and divide by the number of observations. That's your mean. That's your average. And the average is not resistant to outliers. So this is what we're talking about. So median is resistant to outliers because here's a huge outlier right here. This 10th observation is an outlier. It is not present in the second in community B. Community A has an outlier for home price. Community B does not. But the median for both of these communities is identical. It's 21,000. That shows you how the median is resistant to outliers. That's what that means. Now, mean, on the other hand, is not resistant to outliers. If you have an outlier in your data set, the mean is going to respond to that outlier. It's going to radically change the mean depending on if your outlier is higher or lower, right? It's going to just really shift where the mean is because the mean is going to take that observation into account mathematically, whereas median does not. So that's why the mean that's why taking the mean house price of a given area may be a very rough estimate, because in fact median may give you more resistance to possible outliers higher or lower. So again, this is from the textbook, but it just says the same thing. Basically, the mean is, of course, you sum all observations, divide by the number of observations, and there you go. And so once you have your mean, you can begin to think about measures of dispersion, because our measures of dispersion are measures of dispersion around the mean, and that's important to realize. Range is quite simple. It doesn't have anything to do with the mean per se, but variance and standard deviation definitely do have something to do with the mean. And so that's why taking the average, understanding what the mean is for a given variable or a given set of observations, becomes extremely important in the long term. And so let's go forward. So the range of any given set of observations is just the simplest measure of dispersion you can imagine. It's basically just the difference between the maximum of your variable and the minimum. And it basically describes the extremes of the data around a typical case. So you may say, oh, we have a range of 57, and that tells you how widely dispersed your data. A range of 100,000 tells you how widely dispersed your data are. So in some sense, again, much like mode, not very sophisticated. It's not going to give you a lot of very helpful data, but it is going to give you something. And again, all we're trying to do with these measures of central tendency and dispersion are to get some analytical leverage over describing what your data are doing and how they are arranged. We're not testing relationships here. There are no statistical tests involved. This is all about description. All about description. Now, variance is a little different than range. Variance is a very important calculation. And variance takes into account all the values in a data set, so that we're going to use the mean. There are two formulas to calculate variance, just like with mean. We have a sample formula and a population formula. The only difference between variance for sample and variance for population is that we subtract 1 from the sample size in the sample version of the equation. So let's take a look at what that means. So variance is calculated as follows, and variance is this fellow here. This is for a sample, by the way. Sigma hat. Anytime you see a hat, the little hat here, that means we're talking about the sample. And so we have sigma squared is the sum, right? The sum of all observations minus the mean. So anytime you have a bar, that means it's the mean. So y bar, y is our variable that we care about. So the sum, sigma, of all observations. So what you do is you take each observation, subtract it from the mean, you square that, and you divide by the number of observations minus 1. Right? And so to simplify, again, do not worry. Do not worry about these Greek letters and others. It's not important. What is important is that you understand what a variance is. All variance is it is taking a measure of each observation's distance from the mean. How far away is any given observation's distance? What is the variance of this observation from the mean? That's all it's doing. And then that leads us, variance is important because variance leads you to standard deviation. And standard deviation, because it's using variance, takes into account all the values in a data set, and also because it's using means, because again, means do that. And there are two formulas, just like with variance, just like with means. You have the sample standard deviation, the population standard deviation. And again, like variance, the only difference between these two calculations is that we subtract 1 from the sample size and the sample version of the equation. So this is what sample standard deviation looks like. This is what population standard deviation looks like. So what is standard deviation? So let's go back and look at variance. See how variance, you've got all this mumbo jumbo going on, you do all this stuff, and it has a little like squared sign here. So variance is sigma hat squared. Well, this is sigma hat. So all of standard deviation is a sigma hat. It's basically the square root, as you see here, of the variance. That's what standard deviation is. And so the question then becomes, why do we care about variance or standard deviation? Because we care about variance because to get to standard deviation, we need to know the variance. It's just a statistical trick. So the question really becomes, why do we care about standard deviation? And standard deviation is important, and this is an example of how we might get there, because standard deviation is important because we want to be able to make claims about data that we see. So if we have observations, right, and we are going to try to make a claim about any given observation based on the overall sense of the data set, then we have to be able to use these analytical tools like standard deviation, which tells you how far away something is from the mean. And so this would be the observations right here. So we have an observation of a given variable. So variable called x has an observation of 1, observation of 3, 5, 7, 9, right? And so then the mean of this data set, there are 5 observations here. The mean of that data set is 5. And so what is the distance? So x minus x bar. So 1 minus 5 is negative 4. 3 minus 5 is negative 2. 5 minus 5 is 0. 7 minus 5 is 2. And 9 minus 5 is 4. And so then what is when you square that, what do you get? You get 16, 4, 0, 4, 16. Oh, look. And then the sum of all this is 40. So this is the sum of that calculation. It's 40. Divided by the number of observations is 5. And then we come down here and we take the square root of 4. And the square root of 4 is going to be your answer. That's the variance right there. And so the sample, you do the same thing except so this would be the square root of 10. And that's just going to give you a little bit wider standard deviation, a little larger standard deviation. All right? So that's what that is. So variance and standard deviation is used in variance is used in many statistical applications. You will rarely ever need to use the variance per se, but you will use standard deviation to summarize data, and because standard deviation is the same unit as the mean. And if X describes mean income, we could say the mean is 50,000 with standard deviation of 15,000. So let's just back up. So let's go look at some graphs. So why do we care about all this? What we're trying to demonstrate is a normal distribution, right? And so this is our friend sigma, right? So this is the standard deviation. And so if you have a normally distributed variable, if you have a variable that is normally distributed, what that means is that it has a mean, the mean, median, and mode are all the same observation. So if you have a given range of data, you calculate the mean, you calculate the median, you calculate the mode. It's all the same. Like, for instance, in our previous example with the home price is 21,000. Be the mean, median, and the mode. Although the mode in that sense would be, maybe it's not the mode, but in that exact example, but the mean and median would be the same thing. If you have a normally distributed observation, then what we know, as the number of observations increases, we have great confidence. We can have we have 95% confidence that 95% of all observations will fall within 2 standard deviations of the mean. Above the mean, below the mean. 95% of all data. So only 2.5% are going to be out here, and only 2.5% are going to be out here, presuming that your data are normally distributed. So you have 68% within 1 standard deviation, 95% within 2 standard deviations, and then you have 2.5% out here and 2.5% out here. These are the properties of a normal distribution, and that's why knowing what the standard deviation is so important. Because now that we know, in a theoretical sense, and this is the theoretical graph here, right? You have everything, the mean, median, mode are all the same observation. 95% of observations fall within 2 standard deviations of the mean. Presuming that we have this, then what, although I will say that these two things are mixed up, so these are wrong. But presuming we have this, once you have a true measure of the mean and standard deviation, you can then test them against this theoretical construct. And so that's why we want to use this. And so if you have a perfectly normal distribution, you will have a bell curve like this, right? Sometimes you have a rectangular distribution. This happens when you have, usually when you are using a variable that is not interval or ratio. Interval or ratio variables, remember levels of measurement, are almost always, presuming that you have more than about 10 to 15 observations, they will begin to approximate a normal distribution, most likely. Sometimes if you have variables that are nominal or ordinal, you're going to have rectangular distributions. And then sometimes you can have interval or ratio variables that have skew in them one way or the other. Left skew or right skew, right? So you can imagine if the y-axis down here was our housing prices in the Bill Gates example, or the community A would be, this would be 200,000 down here. So it's going to drive the mean. So this is the tip of the highest point of the distribution is where your mean is, and this is going to be where the mean is in our our community A example, right? So that's bad news. Whereas you can imagine maybe we had a house that was, I don't know, 0. Maybe somebody got it for $0. That's going to throw the mean way down here in that same example, community C, which didn't really exist, but we'll just say hypothetically. And so both of those are going to have skew in them. And so that's going to change the distribution. But we only know that there's skew if we know what the standard deviation is of a given set of observations. And if we can then measure the distribution based off of the mean and standard deviation. Because as we know, this is what a normal distribution should look like. This is how we'll know if a distribution is normal or not. You have the mean, you have the standard deviation. If there's skew, we can measure skewness and kurtosis, but if there's skew, then one of the ways we can find that out is with the mean and the standard deviation. But as I said at the very beginning, if you are going to be describing your data, of course, mean, median, mode are going to be very, very important. Standard deviation, very important tool to use when describing the distribution of your data. However, graphs can be really, really important. And graphs it's important for you to know how to read graphs, and it's important for you to know how to make your own graphs. And so this is really important. And so these are some examples of what we can think of as graphs that may be good or bad. And so these are from the textbook, and I just want to talk about a couple of them right now. So here we have two graphs that demonstrate the distribution of CO2 emissions from 1958 to 2010. And the question is, do these graphs demonstrate dramatic climate change from 1958 to 2010? Well, it's a very good question. And so numerically, we could look at this numerically, and you might have some answer or another. But then we might also want to look at this graphically, which we have here, and we'll look at the x and y axis. So the x-axis is here, and the y-axis is here, right? And so if you look at the x-axis, the x-axis for both graphs is the same. And so what we wanted to concentrate on is the y-axis. What do you notice about the y-axis in graph A and graph B? Well, In graph A, the lowest value is 100, the highest value is 500. In graph B, the lowest is something like 320 and the highest is 360. So obviously the range, right? So the range, going back to range, the range of values on the y-axis is different in both of these graphs. And so graph A looks much less alarmist than graph B. Graph B, look, and then of course you have the ups and downs. So you might say, oh, what's causing this? These fluctuations. What we see is that that's because of seasonal changes, right? So CO2 goes up in the summer and down in the winter, and what have you. And I think, if I'm not mistaken, the maximum number of parts per million, sort of the problematic zone, is something like 400 parts per million is sort of the bad zone for CO2. And so if you were trying to make the case that having 400 to 450 parts CO2 parts per million in the atmosphere is a problem, then this graph here is not going to show you that, how close you are to that. And this one doesn't either. So that's one of the things, right, is you may want to put in a little notation here, be like, this is 400 parts per million, 400 parts per million. But the point is that both of these graphs are telling you the exact same information. This one looks like a much larger increase over time than this one because of the way the y-axis is situated. So you just have to know that. I mean, there's nothing wrong. Both of these graphs tell the story, and both of these graphs demonstrate that CO2 emissions have gone up. It's just that from a visual point of view, this one looks much more significant. This one looks much more significant than this one does, but they both tell the same story. Now here's a bar chart, or a histogram bar chart, of party ID in 2005, and this is from the United States Citizenship Involvement Democracy Survey. And this shows you the distribution of American party ID from strong Republican to strong Democrat. And so again, this is one of those that may have a rectangular distribution, because this is a categorical variable and a nominal variable. And so, because each of these are sort of named categories, there's no distribution here per se. And so what you see is that in 2005 and 6, we have significant numbers of people who are calling themselves Democrats or strong Democrats. Fewer people calling themselves Republicans or strong Republicans. And then there are, a good bit of independents, right? And so these lean Republicans, lean Democrats, if you combine them all together, this is sort of your moderates here. And so this is a bar chart. So this sort of gives you a sense of where people are on party ID, or 15, a little better than 10 years ago. And your interpretation of this could change depending on how you want to interpret this. What you see is that most people call themselves Democrats in 2005, and that is reflected in basically the 2006 congressional elections. Remember, that was when Democrats took over the House and Senate for the first time since 1994. In that election, that was a midterm election. Presidential parties typically have a difficult time in midterms. That was certainly true in 2006, 2010, and 14. We shall see if it holds up in 2018. All signs are pointing to that it will, but we'll have to wait and see. Now here's a dot chart. Now dot charts are really good if you have a interval or ratio level variable. So this is what we have here, union densities here on the x-axis. And on the y-axis we have a nominal variable, right? Country, what country, basically the variable label will be country, and each of these observations are different countries. So dot charts are really good for that kind of analysis. And so again, this is sort of a description, like what states have high union densities? Well, Sweden has a high union density, Finland, Denmark, it looks like here. Who is this? Belgium and Norway. And actually, if you go back and you look at that initial chart of Gini coefficients, my sense is that states with higher levels of union density are also states with lower Gini indices, Gini coefficients. And so if you were interested to make the case about, equality across the world and unionization, this may be some interesting data to look into. The extent to which countries have unions and the extent to which their societies are considered more equal. Again, not to endorse or not endorse unions, but that is an interesting observation here. So you can see some of these states that were lower on the Gini index. The United States, for instance, very, very low units. Although Spain, here they are. They're sort of in the middle there. They're the lower quartile notation. And then France, although France was one of the more, it was the median, right? France was the median Gini index, sort of a low union density, sort of interesting. Anyway, just some, again, what is the point of this? Your mean, median, mode, interquartile ranges, standard deviations, all of these things, dot charts, graphs of this nature. This is all about description. I cannot tell you anything for sure about whether or not the United States has a more unequal society because there are fewer unions. I can't say anything about that. All I can say is that based on the data available to us in this dot chart and in the previous chart that showed us Gini indices, what I know is that the United States is at the low end of that sample of countries in terms of equality. So we have a more unequal society, and I can tell you that we have a relatively non-unionized society. That's about all I can say, right? And so as a result, if there's more to say, we have to use different statistical tools, but that, for descriptive statistics, is about all we can do. So this is a great chart that's combining a lot of stuff in one. I really liked it a lot. Figure 11.8, or 11-8 from your textbook. A histogram of women's ages and a normal distribution for comparison. So this is a bar chart. Right, it's got your median, your interquartile range, your mean, standard deviation, all this stuff. So this chart shows you a lot of great information, right? So this shows you the distribution of ages in the 2004 national election study. This is the longest running survey in American politics, the NES. And then it shows you a normal distribution around that. And then it gives you an interquartile range that you can investigate for yourself. So the average age is 47.9. The median is 47. That tells you right there. The mean and the median are very close. That tells you this is very likely a normal distribution. The interquartile range is 27 years. So 33 to 60. The difference there is 27. And standard deviation is 17.5. So what we know is that 95% of all data, let me get a little calculator real fast, 97% of all data, so the mean is 47.9, so plus 17.5 plus 17.5. The top end is going to be 82.9, right? And then on the bottom end, 47.9 minus 17.5 minus 17.5, 12.9. So we know that 2.5% of the American population, well, actually this is sort of bad because this is of adults, right, of people over age 18. And so because, again, we can estimate from the high end, like we know that only about 2.5% of Americans are older than 82. So that's something we can know. But we don't know about Americans younger because, you see, no one under the age of 18 can take the survey. So that makes life somewhat difficult. That's why the bar chart cuts off right here. It cuts off because we can't survey people lower than 18. But we can survey people up to, death or however old you are when you die. So that's good. But so we can tell some things about the American population, or at least women's ages, in this survey based on this information. So again, what is all this about? It's about describing the data. It's about description. There's no statistical test in here. There's no analysis per se. It's just description. It's a type of qualitative analysis with quantitative information. So that's what descriptive statistics are all about. Mean, median, mode, range, variance, standard deviation, and interquartile ranges are all about descriptive statistics and description of your data. So this is the first step. This is how you get started doing data analysis and understanding data. And the most important thing is that you begin to be able to interpret what these things mean. Because you're not going to be doing this for your own paper, but you will be engaging with this kind of information in other places and in future classes. So you need to get used to it now. All right, that's it. That's all for Chapter 11. Questions or issues, send me an email. We are scooting on through. So Module 4 is chapter 11 and 12. So look for lecture 12 as well, and email with questions or issues.